David Smith here with another Flip Classroom math video. Okay people, you've been waiting for this. The moment has come. Today I hit 1,000 subscribers on my channel. Woohoo! Thank you to everybody for watching all my crazy math videos and for subscribing to my channel. This is an awesome moment. I am super stoked to make it to this point. I've been working on this channel for almost 5 years now and uploading videos like crazy. I'm closing on 550 videos, which is quite a big number. And so I just want to take a moment to celebrate, tell you how much I appreciate all of you, because without you, this wouldn't be happening. And get ready for the next David Smith Flip Classroom math video lesson. Woo! Today's video covers another use of the Goodness of Fit test. It's the second in my series on Goodness of Fit. If you haven't watched the first one, I'll put the link below in the comments there or the description, so you can watch that if you feel like you need to before you watch this one. So what we're going to do is we're going to use a Goodness of Fit test. Instead of deciding whether or not it covers a uniform distribution or the data follows a uniform distribution, we're going to check and see if the data follows a normal distribution. So a little different outcome. Instead of that rectangular distribution that we put on that last video, now we're going to be basically checking, does the data follow the bell curve of the normal distribution? So kind of interesting. So our hypothesis is that it does, the data is normally distributed, and our alternate is that it doesn't. Pretty simple, pretty straightforward. Okay, so I've outlined a bunch of steps here. I'm going to explain those steps, what they are, briefly, and then we're going to do them with an example. Okay, so let's get started on that. You're going to use the observed values for each category in your L1 or column 1 on your Nspire. So you're going to just put those values directly in the calculator. They're going to be given to you. Now what we need to do is use normalcdf to find the probabilities for the outcomes in each of those categories. So if the data was normally distributed, there's a certain probability that you could say you get a certain number of outcomes in each category based on where it is in the distribution. So you're going to do that. Then you're going to use those probabilities to calculate the expected values. So you're just going to multiply the probability times the total number in your data set, and you're going to get the expected values, which then go into L2 or column 2 on your Nspire. So now you have your observes and your expecteds. Now what you're going to do, you need, before you do your calculation, you need to determine your degrees of freedom. And that's just, in the case of doing Goodness of Fit test, we call that variable V, and it's just the number of categories minus 1. So now you have everything you need to use your calculator to find your chi-square and your p-value. And once you do that, then you're going to compare that to your critical value given in the problem and your significance level also given in the problem. And then you can accept or reject the null hypothesis or H0. So that's the overall process. Now what we're going to do is do an example with data, and I'll show you how that looks. All right, let's look at the setup for our problem, and then we'll jump into the data. So here's our prompt, basically. Scores on an IQ test are said to be normally distributed with a mu, mean, of 100 and sigma, standard deviation, of 10. We want to check to see if this is true. So the first thing, we're going to harken back to the previous chapter in our book to just state this situation that we have. Random variable x is part of a normal distribution with a mean of 100 and a standard deviation of 10, or a variance of 100. Okay, so the test is given to 200 students. Okay, so that's what our data is going to be comprised of. Now, the hypothesis, the HO, is the test results are normally distributed. And then finally, the alternate is that they're not normally distributed. And so we're going to do our test to find out which of these things are true. At last, some data. Okay, so I did start by rewriting our statement of our situation with the normal distribution, mean of 100, standard deviation of 10. We're going to use this in just a sec. So here's our scenario. Scores. Now, we're aggregating the scores in ranges, which are going to function as categories. Okay, so here's our observed values. We had 5 in the less than 90, 14 between 90 and 100, and so on. And then, of course, we know, I can go ahead and put this, we've been told that is 200. So if you add all these up, you're going to get 200. Okay, so before we go any further, I love to do this thing I call data snooping. Now remember, your normal distribution should look like that. Evenly shaped bell curve, and in our case here, there is our mean, okay? So there should be an equal number of values on this side of the mean and on that side of the mean. Now look at these numbers and tell me if you think that's going to be true for our data set. And I think it's pretty obvious that it's not going to be true. There are 19 below the mean, and then all of these are above the mean. So there's way more data over here. So this is not going to be a normal distribution. You can see that right from the data. However, we're in math, so we want to quantify that, and we want to answer it conclusively rather than just from a data snooping perspective. Okay, now it's time to calculate our probabilities for each of the category. And yes, this is going to be a fair amount of calculator work, but once you get into it, it actually goes fairly quickly. So we need to use normal because we're testing for normal distribution, and we need to use CDF because we're testing for ranges of probabilities. So you're going to get one calculation for each of our categories. So check this out. I'm going to use normal CDF, and I'm going to use my 100 for my mean, 10 for my standard deviation. In this case, my lower bound has to be all the way to negative infinity. So on most calculators, we enter it like this or some form of negative times 10 to the 99, negative 1. And that gives us our lower bound, which is just forever negative. Our upper bound is going to be 90, because that's at most what we want. So go ahead, pause your video, and get out your calculator, and go ahead and find that probability that a result is going to be less than 90 if this was a normal distribution. All right, so when I do this, I get 0.159 as my probability for being less than 90. If you didn't get that, really good, go back in there and give that a shot. You do want to be able to use your calculator to find this probability if this is a normal distribution. And I'll put a link to that video in the comments or the description below. Okay, next step. Now use this probability to find the number that we would expect if the normal distribution happened. So we just got the probability, but the calculator is going to want observed and expected. So the key thing you have to remember is we have a total of 200 people in our sample. So go ahead and use that probability and find your expected value. All right, this is a very straightforward calculation. You just multiply your probability times your total, and that gives you your expected value. So if this is a normal distribution, then we would expect to get 31 people in the less than or equal to 90 category. And already we're starting to see a pretty big difference. We got 5. You would expect to get 31.7. So, okay, clues are abounding. All right, so now what I'd like you to do is go ahead and finish the table. You're going to need to do a probability calculation using the standard normal or the normal distribution, normal CDF. Figure out your probability, multiply that by 200, and that will give you your expected value. So go ahead and finish out that table. All right, here is what I get. My values fall right there. Now I want to make one comment that I didn't cover in that last, or didn't show up when we calculated our first row. So when you start doing the subsequent rows, your lower bound is specified by the range. So in this case, the lower bound is 90, the upper bound is 100, lower bound is 100, upper bound is 110, and so on. And that gets you your probabilities using the calculator. And then, of course, you just multiply the probability times 200 to get the expected values for your table. Whew. Okay, before we jump into the calculator, we need our degrees of freedom. But before we do that, we need to adjust our table, because there is a condition that you've got to remember. And it's kind of nitpicky, but let's take a look. The condition, the requirement is for each category, the expected values have to be at least 5. If they're less than 5, you combine them with the next one up or the next one down if you're working from the top, until that last category is more than 5. And this has to do with the data and the amount of data in a category to make it significant, to make it work with the analysis that your calculator is going to do. So let's take a peek here. our greater than 130, our expected is a little more than a quarter of a student. Okay, so that's definitely not 5 or bigger. So we would have to add that to this category. But when you add 0.270 to 4.28, you're still going to be less than 5. So that means we have to add this and this to this category. And we notice for sure that's going to be bigger than 5 because it's already 27.2. And then we're going to have to combine these categories into this one. So this would become just x is bigger than 110, and then we would put all of these observes into there. So what I'd like you to do is pause your video and do that crunching and see how far you get. Okay, when I add these together to that one, I get 31.75. So here's what I'm going to do. I'm going to go ahead and get rid of this and put 31.75 there. Now that probability is going to be wrong now, but that's okay. And then we have to add our observes also to that. So go ahead and pause the video, get that out. Okay, so our table has been revised. We now just have 4 categories with below 90, between 90 and 100, between 100 and 110, and above 110. And now we know we have observed for this category is the combination of 110, 120, and 130. And so now our observed is 107 for that, and our expecteds are 31.75. Now we could find this probability in the old way, multiply by 200, and that should confirm that number, but not necessary, because these are the values that we need to do our chi-square goodness of fit. So now we can find our degrees of freedom. So remember, we use V, and it's n minus 1, and n is the number of categories. So we have 1, 2, 3, 4 categories, minus 1 is 3. So now we have our degrees of freedom. Okay, so what I want you to do is pause the video and find your chi-square and your p-value for this scenario. Okay, we're at the end of this calculation. So when I go into my calculator for my chi-square, I get 245. Well, that's kind of a big one. I don't think we've gotten chi-squares this big before. So there's a chi-square is 245. My p-value is 7.89 times 10 to the minus 53. So that's like 53 decimal points that way. Okay, so this number is very, very tiny. Very, very tiny. Okay. So now I'm going to give you our critical value, CV. I like to not write critical value out every single time. So our critical value is 6.251, and our significance level is 10%, which is 0.1. So now I want you to use these values, all 4 of these, to figure out whether you can accept or reject HO, the null hypothesis. So pause the video, think as hard as you need, make your commitment, accept or reject, and come back. This one's a big fat reject, and I guess we're not really surprised that this data doesn't follow a normal distribution, because remember, that's what HO is. It's the hypothesis that the data follows a normal distribution. The alternate hypothesis is that it doesn't, and when we looked at that data in the table, it was pretty clear that it wasn't going to follow a normal distribution. However, we just proved that. Okay, so reject, because chi-square is greater than the critical value. Oh yeah, 245, 6.251, that's bigger. And then also, if the p-value is less than the significance level, and that's a teeny tiny number, certainly less than 0.1. So the p-value is less than the significance level. So this one is one of those ones that you would probably, if you had to make a bet, you could make a pretty big bet that the hypothesis, the null hypothesis that the data does follow a normal distribution can be rejected.